Ever wonder how you get that blazing fast gigabit internet at home? You know, that connection that just flies, letting you stream and game and do whatever you want without a single hiccup? Well, it's not your parents' old copper phone line, that's for sure. It's all thanks to this tiny, almost invisible cable that carries our data in a way that is just mind-bending.
Yeah, you heard that right. We are not talking about shoving electricity through a wire anymore. Fiber optic cables send tiny, rapid-fire pulses of light down a strand of pure glass or plastic. This isn't just an upgrade, it's a completely different way of thinking about data. It honestly feels like magic, and it's the bedrock of our modern connected world.
So that's the big question, right? How does it actually work, and what makes it so much better than what we had before? Well, in this explainer, we're going to dive in. We'll break down how these cables manage to trap light, why fiber is so dramatically superior to old-school copper, and how this incredible tech plugs into the global network that powers, well, everything. To really get why fiber is such a big deal, we need to look at its core advantages. If you put it head-to-head with a classic copper Ethernet cable, fiber just blows it out of the water in 3 key ways.
It really all boils down to one simple thing. Copper? It's all about electricity. Fiber? It's sending actual particles of light, photons, down a tiny, see-through tube. And that one little change, well, that's where all the magic comes from. Let's start with the most obvious superpower, speed.
I mean, the scale here is just absolutely insane. We're talking about potential speeds in the hundreds of terabits per second. And yeah, sure, the light inside the cable is a little bit slower than it is in a vacuum, about 31% slower to be exact, but its ability to carry data, for all intents and purposes, it's limitless. We literally don't even know its full potential yet.
All right, next up, distance. This is a big one. Think about your standard copper Ethernet cable. After about 100 meters, that signal starts to die. But fiber, a single-mode cable can push that signal for up to 100 kilometers. That's more than 60 miles. And it does this with almost no signal loss. The technical term is low attenuation, which is really just a fancy way of saying the signal stays strong the whole way. And last but not least, there's this awesome hidden advantage. You see, when electricity runs through a copper wire, it creates this little magnetic field around it. Now, if you pack a bunch of those wires together, their fields start to mess with each other. It's called crosstalk, and it can corrupt your data. But light? Light doesn't have an electromagnetic field. Zip, zilch, nada. So the signal stays perfectly clean, totally immune to any of that interference.
Okay, so we've established fiber is faster, goes way farther, and the signal is cleaner. But hold on a second. How in the world do you keep light trapped inside a tiny little cable? I mean, why doesn't it just leak out the sides, especially when you bend it? Well, the answer is pretty cool, and it all comes down to a neat trick of physics.
It's all thanks to something called total internal reflection. Here's a way to think about it. Grab your phone and shine its flashlight at a window. If you shine it straight on, the light goes through, right? But what if you aim it from a really, really shallow angle? You'll hit a point, the critical angle, where the light stops going through and instead reflects off the inside of the glass perfectly, just like a mirror. Fiber optic cables are basically built to force that to happen, again and again and again.
So, inside the cable, it goes like this. A little pulse of light shoots into the very center, which we call the core. As soon as it tries to escape, it hits the outer layer, that's called the cladding, at that exact critical angle, and boom, it reflects perfectly, bouncing its way down the line. It's basically trapped, ping-ponging its way to the destination, even if the cable is twisting and turning.
Okay, so now that we know how it works, you should know that not all fiber is the same. You'll basically find 2 main flavors out there: single mode and multimode. They're both built on that same idea of total internal reflection, but they're used for totally different things. And it all comes down to one simple design choice.
And that choice is the size of the core. Multimode fiber has a pretty wide core. This means the light has plenty of room to bounce around at all sorts of different angles as it travels. But single mode? Its core is impossibly thin. I mean, so narrow that the light literally has no room to bounce. It's forced to go straight down the pipe, like a laser beam.
And that one tiny difference changes everything. Multimode, with its bigger core, is cheaper to make. A lot of it is even plastic. But because the light is bouncing all over the place, it can't go very far, maybe a few hundred meters, tops. Single mode, on the other hand, with its super precise glass core, yeah, it's more expensive. But forcing that light to travel in a straight line is what lets it hit that insane 100-kilometer distance with even more bandwidth.
So you might be asking, why would anyone use the shorter range one? Well, multimode is the unsung hero of the data center. It's absolutely perfect for connecting things inside a building. You know, linking up network racks, connecting servers to storage, or running a connection between floors. You get massive bandwidth, and you don't need it to go for miles.
Now, single mode, that's the long-haul champion. This is the stuff that connects buildings all across a college campus. It's what your internet provider uses to bring service to your entire city. And get this, it's what they run in those giant armored cables at the bottom of the ocean to connect whole continents. When we talk about the backbone of the internet, we are literally talking about single-mode fiber. All right, so at this point, you're probably thinking fiber is just better in every single way. It's faster, it goes farther, it's more reliable. Which leads to a pretty obvious question, doesn't it?
If it's so great, why do we still even have copper Ethernet? Why does your computer have that big, chunky Ethernet port and not some tiny, fancy fiber one? And the answer, as it often is, comes down to some very simple, practical reasons.
Here's the bottom line. Copper is cheap, it's tough, and it's just plain easier to handle. You can't just go online, buy a crimping tool, and make your own fiber optic cables in your garage. Splicing fiber is a delicate art that takes special training and expensive gear. But copper? It can take a beating, and that classic RJ45 plug, well, it's everywhere. For plugging your computer into the wall, it's the simple, good enough choice.
Okay, so when you do use fiber, how do you actually connect it to anything? It's pretty clear it won't jam into a regular Ethernet port. So let's take a quick look at the plugs and ports that make all this work.
You're going to see a few different kinds of plugs, but these three are the big ones. The LC connector is pretty much the modern standard. It's nice and small and it clicks right in. You might still see the older, kind of squarish SC connector, or even the old round SD connector that you have to twist to lock. Really, the only thing that matters is making sure the plug on your cable fits the hole in the switch.
And where do these things plug in? Well, on a lot of professional network switches, you'll see these special slots called SFP ports. SFP just stands for Small Form Factor Pluggable. Think of it like a wildcard port. You can pop in an SFP module for copper, or you can pop in a different one for fiber. It's a super flexible way to let a switch talk to whatever kind of cable you've got. And hey, here's a little pro tip for you. If you're ever in a server room and see a bunch of cables, the colors can tell you what you're looking at. If you see a bright yellow cable, that's almost always single-mode fiber, the long-distance stuff. And if you see an aqua blue or orange cable, you're probably looking at multimode, for those shorter runs inside the building. It's a handy little visual shortcut. So all this brings us to one last big thought. Fiber optics went from being this weird science experiment to being the literal foundation of our entire data-driven world. Copper definitely still has its place, for now, but when you look at the raw speed and just sheer capacity of light, it's undeniable. And as our world gets more and more hungry for data, you really have to ask yourself, are we heading toward a future where everything is connected by light?